You write code, run your unit tests, and watch every checkmark turn green. The logic clicks into place, and the architecture feels complete. But building software introduces a specific cognitive bias. When you create something, you unconsciously design tests to confirm that your logic works as intended. You tread lightly, rarely seeking to destroy the edifice you just built. This bias creates a fragile sense of perfection. The code functions flawlessly, but only because it exists inside an artificial, tightly controlled vacuum, a sterilized environment where every input is expected. Self-testing fails to account for the one variable a developer can never accurately simulate: the unpredictable, messy friction of a real human being. The moment that pristine software is handed over to an actual user, it collides with reality, and very often, it breaks. What the user experiences in that moment of failure is a symptom. It is the outward, visible manifestation of a problem: a frozen screen, a crashed application, or an unresponsive button. But that visible glitch is not the actual error. The cause is a hidden logical flaw buried deep inside the software architecture. This creates a gap in knowledge. A user can easily describe the symptom they experienced, but they lack the access and the training to identify the underlying cause. Software engineering requires an investigative bridge to connect a highly visible user complaint to a silent logical flaw. To safely harvest these user symptoms without ruining a product's reputation, developers use phased testing environments, starting with the alpha test. Look at the split-screen model. On the left, the alpha environment is a controlled setting at the developer's site. Notice the observer icon. The developer watches the user interact. If the user deviates from the path, the observer logs the resulting symptom. Eventually, the software enters the beta test. This is an unmonitored environment sent directly to end users. Customers run the software across chaotic, randomized hardware and network variables, generating scattered symptoms that ping blindly back to the central hub. Neither alpha nor beta testing actually fixes the code. They are symptom harvesting engines, gathering the raw data required to begin a focused investigation. While testing phases are systematic and planned, debugging, the removal of the error, is a deeply psychological art. This 3D map illustrates geographic separation. A symptom appears on the surface layer, like this flashing warning. But descending through interconnected logic layers, we find the cause is a broken root node buried deep in the back end, far away from the warning sign. Because the cause is rarely located physically near the symptom, guessing is inefficient. Developers must adopt strategic frameworks to navigate the dark space in between. There are 3 primary strategies for hunting causes, starting with brute force. Brute force relies on a let the computer find it philosophy, flooding the screen with massive memory dumps and runtime traces. This overwhelming volume of raw data rarely identifies the exact cause and usually results in wasted effort. When brute force fails, developers turn to the second strategy: backtracking. This involves tracing the code backward from the symptom. While effective in small programs, this path quickly splits into hundreds of tangled, unmanageable branching paths as the software scales. That leaves the third and most effective strategy: cause elimination. By using binary partitioning, developers systematically divide the architecture in half, testing data to prove or disprove a specific hypothesis until the exact cause node is isolated. Cause elimination transforms guesswork into a repeatable, logical search, providing developers with a reliable way to cross the gap from symptom to cause. There is an old engineering maxim that debugging is twice as hard as initially writing the program. Software engineering is not the simple act of typing logic into a machine once. It is an iterative cycle of continuous observation and investigation. Truly robust software is forged only by exposing it to the friction of unpredictable humans to harvest its flaws, and then applying the rigorous logic of debugging to eliminate them forever.